Hello everyone, welcome to lecture number 4. In this lecture, we will study limit comparison test. The statement is as follows. If series AN and series BN are series with non-negative terms, then limit as n goes to infinity. If limit, here it is, limit as n goes to, if limit as n goes to infinity, an upon bn is equal to c, which is greater than 0, then an and bn, the both series behave alike. So both behave alike, right? So just let me, both behave alike means if the series an is convergent, then by default series bn will also goes to convergence. If the series an is divergent, then series bn is also divergent. That means both are either divergent or both are either convergent. Then second case, if the limit as n goes to infinity, an upon bn is equal to 0 and series bn is convergent, then we can straight away say that series an is also convergent. And the third case, if the limit as n goes to infinity, an upon bn, that limit goes to infinity and series bn is divergent, then we can straight away say that series an is also convergent. So we will see the proof of this theorem. So proof of statement number 1. Statement number 1 says that if limit as n goes to infinity, an upon bn is equal to c, which is greater than 0, then we have to prove that both behave alike. Both behave alike means either both are convergent or both are divergent. So it is given that limit as n goes to infinity, an upon bn is equal to c, which is greater than 0. So we can apply a definition of convergent sequence. That means sequence an upon bn converges and it converges to c. So this would imply for every epsilon greater than 0, there exists n naught belongs to natural number such that modulus of an upon bn minus c is less than epsilon for all n greater than equal to n naught. This is true for any n greater than equal to n naught. So this would imply this modulus has a nice property. If the mod is less than epsilon, then that number must lies between the minus epsilon to plus epsilon. So this would imply that an upon bn minus c lies between minus epsilon to plus epsilon. So an upon b is less than minus epsilon less than an upon bn minus c less than plus epsilon for all n greater than equal to n naught. So if I add plus c on both sides, then I will get c minus epsilon is less than an upon bn is less than c plus epsilon. Now epsilon is any positive number and it is given that c is also positive. So we will take epsilon as c by 2. So this would imply, now here if I take epsilon as c by 2, then c minus c by 2 is c by 2 less than an upon bn, which is less than, here c plus 2 plus epsilon is 3c by 2. Multiply this inequality by bn. Since bn is non-negative, so it is that inequality remains same. So we will have c by 2 times bn is less than an is less than 3c by 2 times bn. This inequality we will label as or called as a capital A inequality. Right. So now we have to prove the first part. So consider this part. So if the series Bn is convergent, then definitely 3c by 2 times Bn is also convergent. And if we apply the ratio test, if we apply the comparison test, then we can straight away say that An is also convergent. So series Bn converges implies series An convergence. So let's write down that. If series Bn converges implies series 3c by 2 times Bn also converges. One should know the reason for this by algebra of series. So this would imply series, let's go to the previous slide. If this is convergent, then this is also convergent by comparison test. Then series An converges by comparison test. So if the series Bn converges, then series An also converges. Now this, what if the series An diverges? If the series An diverges, then we could see that if we will consider now this part. If the series Bn is diverges, now let's write down this. Here we will complete it. So second, if series Bn is diverges, so let's come to that inequality. If the series Bn is divergent, then c by 2 times Bn is also diverges, and by we can say that by comparison test series An is also divergent. If Bn diverges, that means series c by 2 times Bn diverges by comparison test. Series An diverges. So we started if the series Bn diverges, and we have ended here series An also diverges. So from this we can see that both if the series Bn diverges, then series An diverges. If the series Bn converges, then series An also converges. Hence we can say that series An and Bn both behave alike. Second part, proof of statement number 2. Now it is given that limit as n goes to infinity, An upon Bn is equal to 0. That is first part. And it is also given that series Bn is converges. We have to prove that series An is convergent. So given number 1, since limit as n goes to infinity, n upon Bn is equal to 0, so by definition of convergent sequence, we can say that from For every epsilon greater than 0, there exists n naught belongs to natural number such that the modulus of an upon bn minus 0 is less than epsilon for all n greater than equal to n naught. That would imply minus epsilon less than an upon bn less than plus epsilon for all n greater than equal to n naught. That would imply minus epsilon times bn is less than an less than epsilon times bn for all n greater than equal to n naught. You observe that multiplied by bn and bn is non-negative, so inequality remains same. Now, since series bn is convergent, we will consider this part only now here. So since series bn converges, that would imply series epsilon times bn also converges because of that algebra of sequences. And if this series is convergent by comparison test, we say that series an is also convergent. So by comparison test, series an is convergent. This completes the second part of proof. So let's now prove the proof of third part. It is given that limit as n goes to infinity an upon bn converges to infinity. That means sequence an upon bn is divergent. So that is sequence an upon bn is divergent sequence. And in first year BSc semester 1, we know that the definition of divergent sequence. So we can say that that would imply for every, we can say that for every alpha, a real number greater than 0, there exists an n naught belongs to natural number such that an upon bn is always greater than that alpha. That would imply an is greater than alpha times bn. That would imply alpha times bn is less than an. But it is given that series bn is divergent. That would imply series alpha times bn also divergent. So this series is divergent, implies this also divergent. So by comparison test, series bn diverges. This completes the lecture number 4. Soon we will have the lecture number 5, which will only cover the problem based on limit comparison test. Thank you.